Awesome. All right. So this kind of segues into the one stack. So just from my understanding of the internet over spending a number of years, with Victor and Dino going to the IETF. I started, if you remember that speech, Victor, where I tested out the consensus layer on the list discussion, and we got a lot of interest, and that's where I started to realize I think we're onto something here, because the internet right now, it was designed as this closed private network, right? And then later down the line, they decided to commercialize it. And since it was designed to be this open intergalactic network where everybody could communicate with one another openly, right? That openness ended up becoming, a feature and a bit of a design flaw, because we have all these DDoS attacks, we have, ARP spoofing, there wasn't authentication up and down the OSI. And so all these other security, limitations came out. And granted, that's what happens. You when you design something, you don't always know what everybody's going to do with it. I've had that personal experience with designing Nexus. You'll build it the best you can, but then you have to sometimes hire people to attack it, or bring security people in to understand, because we don't always see all of these angles. So over the number of years, playing around with the OSI and then designing the Tritium software stack, it all kind of ended up molding together in this beautiful operating system, right? And as Victor brought up a really important point, that the biggest driver of adoption of TCP/IP was that it was embedded in the original Unix operating system, right? The BSDs. And so that's something that we find is going to be extremely important. And as Nexus is kind of a tool to bring more of our own digital freedom, we need to have it all the way down into this operating system. So, thus begins my story, where I started with game development when I was 11 years old. And then I started learning more and more, right? And then I find out about sockets, and then I get really good at socket programming. And then that drives me into creating the lower level protocol for Nexus. And then, the more I learned, the more I started understanding, okay, wait, we got transport layer, and then getting into IP. And then Dino taught me a lot about how IP works. I remember when we were just talking, and he's like, oh yeah, you can use raw IP packets. I'm like, wait, I can send on layer 3? He's like, oh yeah. I was like, I can make my own LLP IP. And me and Dino, we always used to joke too, where he'd say, oh yeah, when Colin invents IP version 12, and I was like, well, I think we need IP 12 because we need a 256-bit addressing, because we need to address all of these objects and stuff like that. But little did we know that Lisp and all these conversations would grow into this actual new stack, right? So this is the beginning stages, right, of the architecture has been released in an architectural document, right? And that is called the Nexus protocol. So this is going to weave in through the one stack. So what is the one stack? The one acronym stands for Open Nexus Execution, right? The reason it's called the Open Nexus Execution Stack is because we have this additional layer on it that's called the consensus layer. And I'll see how, I'll explain how that weaves together with basically our, OSI and Tritium software stack. And originally the Tritium software stack kind of sat and weaved in with the OSI, but then as it got further and further developed, we ended up combining that together into this Open Nexus Execution Stack. So it's a reference model that's designed to replace the OSI reference model. And one of the big key takeaways from it is that we want to have authentication all up and down this stack, right? And it also takes the Locator Identifier Separation Protocol, which Victor and Dino have worked on substantially for Cisco, and it turns it into an actual stack, right? So it's the fundamental reference model for the Nexus protocol, which is NP. So you're going to have, an NP addressing system, but I'll show you how it works together with a locator. As you remember, Lisp is breaking apart the locator and the identifier from one another. And that's a really, really important use case for the internet. As Victor said, when somebody moves their actual physical location, then the IP address naturally has to change. So if you go from your Wi-Fi to your LTE, or make any sort of change in physical location, you're going to have a totally different address. So if you had some open connections with somebody at that point in time, they're going to be terminated, and you're going to have to reestablish the connections, because the internet and IP itself was designed for these static meshes and nodes, right? And it's topologically dependent. So, some of the original founding principles of the internet being this open intergalactic network are things that inspired me, actually, and inspired me into getting into that type of activism through computers, where, I saw a computer as a tool for freedom, right? But the more and more I learned about it, the more I realized, okay, well, this vision is there, right? But some of the technical implementations are still, lacking slightly, just similar to kind of with blockchain and Nexus, from understanding Bitcoin and the Bitcoin protocol, which, was a beta. It was an alpha version. Actually, if anybody didn't, I've said this before, but it starts with 0.19, whatever. Zero denotes that it's still in beta, right? It's not actually a full new version. So even Bitcoin itself is still kind of in that. And the internet, I wouldn't consider it a beta, but there are some limitations like IP version 6, right? Most people aggregate behind network address translators for IP version 4 because IP version 6 routes haven't been fully updated. And just as you saw, I mean, they introduced TCP/IP in the early 70s, and it took close to a decade for that to fully get proliferated, partially because they had to actually put a requirement on. And that's one of the downsides of having hardware-defined routing, right? Is that you have to actually physically change the hardware, just kind of like, the locator, you have to physically change it. And we're in a new age of having things become more software defined. We see the cloud, we see, all these different technologies that are virtualizing these things. And so that's what this operating system is essentially doing. Is it's for one, it's using the blockchain to authenticate everything up and down, and that's part of the consensus layer. And it's also creating the software defined router. So it, just like the OSI stack, includes 7 layers, but we have included 2 layers from the current OSI. And you'll see what layers those are, because there's no need to throw the baby out with the bathwater. There's definitely a lot of really great technology that's come out of the IETF. So we're kind of cherry picking some of those, technologies that are going to be valuable into this new one stack and driving them forward. So the one reference model looks like this, right? And this is actually showing you the Tritium software stack on the right-hand side and the one stack on the left-hand side. So you'll see how they seamlessly fit together. The Tritium software stack is kind of like sub-layers within the actual main one stack. So the base layer we have is the signal layer. And the signal layer is essentially responsible for your end-to-end communication. And then the locator layer, this is where those packet headers are stripped on and off. And the locators can be many different types. I'll get into those in later slides. And then the identifier layer, this is what you're actually sending the packets to. So as you see, the identifier layer is on layer 3, just as the network layer for the OSI. So this is actually where your IP addresses are on the OSI stack. So for here, this is what you'll be seeing. You won't see any of the locators. Those are going to be kind of handled under the hood, just like you don't generally see a MAC address in your network. You're just connecting to people's different IP addresses. So the identifier will be the equivalent of the IP address, right? And then the 2 layers that we borrow are the transport and the session layer, right? This is for, TCP and UDP on the transport layer. No need to throw the baby out with the bathwater. So it's going to be TCP NP, as you see. And the Nexus protocol is these lower 3 layers right here. And this is the bulk of the routing system: the signal, the locator, and the identifier. And then the session layer is kind of like your socket, your end-to-end session. And that, sometimes is seen as, where secure socket layer happens, TLS, things like that. And then we get to the consensus layer, which this is the bulk of the actual TAO framework. As you can see, we have the ledger layer and the register layer and the operation layer here within this consensus layer. So what this consensus layer gives us is it gives us the capability to do root of trust. And I'll get to that in a bit later slides, but also what it allows us to do is create this software-defined routing system and a virtualized operating system so that we rely on this consensus layer for our common root of truth, right? And then the application layer goes into the API, logical, and interface. So if anybody, when you hear hard fork, that's because there was a change in any one of these 3 layers in the consensus layer, either a ledger layer rule, a register layer rule, or an operation layer. In order for this consensus rules to be updated, everybody has to update the software on the network. So that's one way that you actually are able to gain security from this consensus is you have the consensus required to update to that new protocol and also operate it, right? So it's not something that can just be changed. And the data that goes within the consensus layer that's stored on the ledger layer is immutable. So we can use it reliably, right? And then the application layer, this is the same as the OSI, the top layer, but we break this into 3, where we have the application programming interface. And this is generally an HTTP JSON interface. And the API is going to be built directly into LXOS in the operating system. And that's one thing that we hope, people building applications on top of this consensus layer, you'll get additional layers of security, even for your local operating system environment. So what's the signal layer? The signal layer is responsible for the physical modulation of the carrier wave, right? We're not doing anything with wires. We're doing it all wireless. And part of the reason is because, our wireless technology has finally gotten to that point where we can have a high bit modulation pattern. So it's connected wirelessly with phased array antennas. Now, what a phased array antenna does is it allows you to steer electronically. So normally if you see satellites, you normally have this dish, and this dish has to move, and it points to a certain point in the sky, right? So when it's a geosynchronous satellite, that dish points, and then you can just leave the dish pointed because it's always going to be in the same point in the sky. It's fixed. But when you start getting in a low Earth orbit, you have about a 90-minute orbit around the Earth, right? So these satellites are constantly moving and constantly changing their positions. So if you had a dish, you constantly have to move it to track. If you guys have ever seen those old RVs, or not old, the RVs that have the satellite dish on them, when you park the RV, you got to go point that until you get a strong signal, and then boom, you're good, right? That's just not going to be practical, especially because we envision a lot of this, increasing your connectivity in any type of vehicle, such as, an airplane, a car, or even just, at your home network, right? So phased array antennas give you equivalent gains that you get from satellite dishes, but it allows it to steer electronically. So you have this fixed antenna, and it uses interference patterns. So if you imagine kind of like ripples in a pond, if you have your main signal coming out, but if you dropped rocks on the other sides of that ripple, they're going to push ripples in, right? And those are going to create interference, which is going to almost push that beam and focus that beam at a tighter level, right? And so what that gives us is it gives us high directional gain, which is really important, because when we have high directional gain, you're not going to get as much isotropic radiation. Isotropic radiation means that it radiates out in a type of spherical shape, okay? And, the airwaves can only carry so much, EMF, electromotive force, or, it can only carry so much information before it becomes saturated. It's kind of like, the median, it travels through the ether, kind of like you'd see a ripple travel through a pond. But, there's only so much that can be contained in that before it gets saturated. Imagine just dropping a bunch of rocks, and if each one of those rocks has to have a specific meaning, you have to be able to read that output, and you have too many ripples going on in the pond, you're not going to be able to tell what's what. And that's where you get a high error rate, right? And that's been one of the big issues that, Amos, his discussed Amos Peterson, he's speaking a little bit later about, mesh networks and why they've always ended up failing. Is because of RF saturation. You have too much saturation of the airwaves in high density areas, and the mesh networks just don't work, right? So high directional gain is really important to overcome that, because instead of having these big circular ripples, right, we're focusing them into these really, really tight beams, right? Super highly directional. So for one, we get a very high gain, which means you get a stronger signal strength. Now, what the signal strength means is that's basically from the background noise, all the background ripples, how strong that signal is above that background noise. Because if your signal is right there, like maybe a couple decibels higher, you're not going to be able to tell what's signal and what's background noise. And so you're going to get a high error rate. So generally speaking, you can do a higher modulation pattern when you have a lower error rate or a stronger signal strength. So these phased array antennas need to be anywhere from 33 to 42 dBi. Which is fairly achievable for a phased array antenna and to reach our 500-kilometer orbit. But one thing that's really important about why we also needed these phased array antennas is that gain is going to be important for us to be able to use an unlicensed band. So there's these frequencies that are called ISM, which stands for Industrial, Scientific, Medical, and they were allocated for industrial and scientific and medical applications to not have to be burdened with constantly getting new frequency licenses. So they originally had 2.4 gigahertz. That was one of the original ISM frequencies. If you look at your microwave oven or Bluetooth or any of those other things, it's going to be 2.4 gigahertz, right? And so 2.4 gigahertz naturally, since the 60s or 1956, I believe is when it was allocated, has become extremely saturated. So just like the ripples, right? When you have too much saturation on 2.4 gigahertz, your phone, right? This phone using 2.4 gigahertz, my Wi-Fi is using 2.4 gigahertz. So you got 2.4 gigahertz everywhere. Your microwave oven, right? So 5.8 gigahertz was actually located in 1996 as a means to overcome some of the overcrowded 2.4 gigahertz spectrum. Now, it also has water absorption properties, 2.4 gigahertz. So that's why it became more popular for short range wireless communication, because it does get absorbed by moisture, right? So 2.4 gigahertz does give us a longer distance, but we had antenna gain limits, right? Because we need to stay within the regulated values for emission, right? So using 5.8 gigahertz, we are limited to 1 watt of transmitting power. So with only 1 watt, how do you get that distance, right? 1 watt, if you run it through an equation, it could, if you have a very low gain antenna, you're talking about maybe a few hundred feet, right? But once you start increasing the gain of your antenna, instead of it being this isotropic, right, where it's just spherical, if you imagine it, think of it as the energy dissipates at the inverse square when you have isotropic radiation, right? The point charge dissipates at the inverse square, kind of like gravity. Inverse square just means divided by the distance squared. So, if you're at 3 feet versus, 1 foot, you have 9 times the losses than at 1 foot, right? So you lose it exponentially. So you overcome that with having this high directional gain. Instead of just spraying out everywhere like this, you're focusing these beams in. And so when we have 33 dBi, or even 42 dBi, we actually, the reason I say 42 is because we can get a strong enough signal strength to do 1024 quadrature amplitude modulation. But when we're just doing this 1 watt with 33 dBi, we're able to get, I think it was minus 72 decibels, milladecibels at 500 kilometers. So what that means is that's a fairly decent signal strength. That we can do, lower modulation patterns, probably 64 symbols rather than 1024. But you still can get a very decent link at that level. And then once you increase antenna gains beyond that, you end up with having a larger data rate. So we're following the modulation encoding schemes, which are generally utilized in 802.11 applications, which just is a simple table that tells you what types of modulation patterns you're going to be using at what specific signal strengths, because you require a certain receiver sensitivity to be able to receive that information without it having too many errors in it, right? Because that background noise, if you have too many symbols and too much background noise and not a high enough signal strength, then you're not going to get a good data rate. So the MCS 11, which is the highest code that I was able to find, is currently supported by 802.11ax. Now, I want to be very clear. We're not using 802.11 for satellite to ground communication. We're writing our own protocol for that, and that's part of the signal layer. And we're using the modulation encoding schemes in order to have different levels of modulation, which means that if your signal strength is lower, let's say it's a rainy day, you're probably going to get a slower downlink. But if you have the sun out and it's wide open and you have a really strong phased array antenna, you can get up to 1024 quadrature amplitude modulation. And so based on the 802.11ax specifications, if we're able to get a receiver sensitivity down to minus 52 decibel milliwatts, then we can actually get up to 10 gigabits per second, right? Which is an extremely high data rate. And 802.11ax is starting to prove that. But you have to use 1024 symbols, right? 1024 quadrature amplitude modulation, which I believe is about 11 bits per wavelength. So what ends up happening when you add more symbols with quadrature amplitude modulation is you're able to add more data per wave cycle. And since 5.8 gigahertz is about 5.8 billion cycles per second, and you add 3 extra bits, now you multiply that 3 bits times 5.8 billion, and that's how many more bits that you have. So that's what 18 billion bits, right? So that's what divided by 8, you're at about like 2 extra gigabits, right? 1 or 2 gigabits just from adding those extra symbols. Because when you start multiplying and having a lot of cycles per second, then you're able to get more bits per wavelength. So that was actually really, really pleasing when I started running it against existing specifications and existing hardware, because it really paints the picture of what type of bandwidth we're able to expect. And if you're going to a satellite that's directly overhead, your latency could be less than a few milliseconds because you only have 1,000-kilometer round trip. So we can actually, one of the design goals of this is we can't go backwards, right? This new internet protocol has to be more secure and usable, but also maintain some of the similar data rates that we're used to, right? Without having to go into 5G necessarily. When you start getting into millimeter, wavelengths, they're kind of like a little pea shooter, just boom, it's like if you shoot like think of it kind of like shooting an airsoft gun versus shooting a real gun, right? The airsoft gun goes kind of poof, right? Because it's really lightweight. It doesn't have a whole lot of momentum. And that's kind of how like a higher frequency is. It just kind of goes poof, and it doesn't really go very far, right? So when you start getting into these 5G architectures, millimeter wavelengths, they don't necessarily provide you much value because we need that distance, right? One of the reasons that they're focusing on 5G is so that they can actually put phased array antennas inside the phone, because your phased array antenna size is limited by your wavelength. So 5.8 gigahertz, our wavelength is about 2.8 centimeters. Okay, that's about this big is how big the actual wave is in the real world. So the phased array antenna has to have each element spaced half of that dipole, right? So 100 elements could end up being about 10 centimeters by 10 centimeters, which is about the size of a 1U cube satellite, right? So we can fit about 100 elements per face on that 1U cube satellite. Multiplied by that 6, we can have, close to 600 elements for each satellite with their own, direction, right, that they can communicate with. So this, this frequency also is really important so that you don't have to deal with the ITU, which stands for the International Telecommunications Union. So what they do is they regulate all of the electromagnetic frequencies around the world, because different frequencies can interfere with other frequencies. If you guys have ever seen, it happens with sound pretty easily. If you have a basic, let's say you're in this semicircle and you stand right here and you try to clap, you actually won't hear anything if you stand in the right spot, because the wavelengths, as you send it out, they cancel each other out, right, and nullify each other. And that happens in RF. That's where you get signal jammers, radar jammers, for COP radar, stuff like that. You're just creating a signal that's the exact opposite wavelength that wipes that clean, right? So the International Telecommunications Union has justification to regulate these different frequencies because they have a lot of critical infrastructure that relies on them, such as radar, right? So we had to find a way around that. And that was always the biggest difficulty, right? Because OneWeb, for instance, I don't believe even got their full constellation allocation license, and it can cost, millions and millions of dollars. And the other downside of it too is it has to be registered to someone or some organization. And that just was not within our model, because, continuing that original vision of the internet, it's supposed to be a federation or a confederation. It's supposed to be, a loose joint of different organizations combining together to create this global network. So if we rely on this centralized frequency allocation, then at any point in the future, even if, for the next 100 years, we run the organization correctly, if, they continue to own it and somebody does try to take over and turn it into an oligarch, then they can limit that frequency. And a lot of times, people that own a frequency license could sublease that frequency out and let other people utilize it. So this allows us to do it without any of that. None, zero, right? We can run unlicensed. All we have to do is accept harmful interference from other devices and stay within the 1 watt transmitting limit. And 5.8 gigahertz was really important too, because that gives us a really high throughput, and we don't have any limitations on the antenna gain. If we use 2.4 gigahertz, we would be stuck at 6 dBi, which is nothing, right? We need 33. And so 5.8, in order to incentivize people to use it more, they allowed unlimited antenna gains, right? And if you look back to, there is a lot of amateur satellites that use 5.8 gigahertz. It's actually a fairly well used satellite frequency, right? Which is really cool. So the ISM frequency is really important so that anyone can deploy a ground station. Anyone can develop a ground station. Anyone can deploy satellite, and there's no central need to get permission from someone, right? And using these high directional gains with these phased array antennas, we have that mobility, and we also have the gain, and then we have an incredible data rate with 8 spatial streams, as I was saying, and 1024 symbols, 1024 QAM. You can get up to 9.6 gigabits per second, which is an incredible throughput. And they're starting to see that with, when you have a high enough signal strength with 802.11ax. And that's where I got the modulation encoding schemes from, is 802.11ax went all the way up to MCS 11, where they're starting to play around with 1024 quadrature amplitude modulation. And as we get further progressed, right, we can actually continue to improve these modulation patterns, quadrature amplitude, maybe go to 1024 or 2048 or 4096, and improve those chips. So without actually having to change our frequency, we can just change the way that we're modulating the frequency, and we can get extremely high data rates. So what's the locator layer? the locator layer is responsible for routing the packet to the current geolocation. So that geolocation, it can come in many different forms. The three main locators that we're going to talk about are geospatial locators, wide radius locators, and internet protocol locators. That would be GSL, WRL, and IPL. So a geospatial locator is kind of like the heavier duty one. One reason that we have this type of aggregation in the mapping system is because since it's a GPS routing system, we don't want that creating any privacy vulnerabilities. So the only person that will actually have your geospatial locator, which is your precise locator that is enough information in it to get the packet to your physical location in the mesh from a ground station, the only people that will have that are the ground stations that are physically within line of sight of you, right? Because in order for the RF to travel, you have to have a line of sight in some way, shape, or form. So these geospatial locators contain all of the details of information of where the specific person is, but they don't give it away on the global mapping system where you are. And this was also another really important point because Victor brought it up. You know, I originally was saying, hey, you know, stateless routing system. And I was just like, whoa, how do we stateless routing system, man? This is so cool. And then he's like, what are you going to do about the mapping system? I was like, oh man, you're right. And, you know, another thing too, you know, well, what do you do if somebody tries to monopolize it, right? So Victor brought a lot of really good points to it that really help form the architecture. So, you know, the mapping system is going to exist in a compressed form on the satellite constellation using wide radius locators. So essentially a ground station will contain aggregated information where it will tell the satellite constellation what specific identifiers that it is servicing. And you use the identifier as your index, and then the packet needs to go to the wide radius locator when it's first sent out, right? And that's what's important about the locator layer is it has your packet, your main body of the packet, and then these headers, right? And as Victor was saying, the header contains the stateless metadata where it has all the information it needs to get to its final destination. The locator layer on Nexus is going to be constantly stripping these off and re-encapsulating them. It's a Lisp concept called re-encapsulating tunnel router, and that's what Lisp currently does in order to traverse network address translators. But we're going to actually use it to allow interfacing between any different type of network as a type of ad hoc network to initially form, where you'll have the same common interface and you won't know that you're connecting to, you know, an NPU or an IP or whatever, because you're going to be dealing with these identifiers. And that's where Lisp becomes really important because it gives us this static location, right? So this static identifier. So if in the day in the life of a packet, let's say I need to send a packet over to Victor in San Diego, I will have, you know, my current local network, okay, which that's going to be running 802.11. Okay, a Wi-Fi. That's my local client connection to my ground station, right? I'm going to have a ground station, which is just going to be a little phased array antenna and a computer. That's all it is, right? The phased array antenna is the most important part. You put the phased array antenna up on the side of your house, your roof, whatever. And so I send my packet over 802.11 to the ground station over regular Wi-Fi, and the ground station is going to pick up that packet and it's going to find the identifier that it's addressed to, and it's going to have a local map cache and it will have a global map cache. So if it has a local cache, it'll say, oh, okay, I know the WRL where Victor is, right? And the WRL could be something as large as San Diego. Victor's in San Diego. That's all I know. So I send the packet, my ground station finds that initial locator, right? And it appends that header onto the packet with the wide radius locator. And then it shoots it up to its nearest satellite, right? And the satellite will then receive it. And the satellite will have knowledge of its peers that it's connected to, kind of like a distributed hash table where you don't necessarily know where in the entire system the data is, but you know in the direction that it is. You have hints, right? So, you know, a satellite up in there will be in the form of a ring, right? Satellite rings. I send it up and the satellite knows I either need to go this way or I need to go this way. And so it sends it to its nearest satellite in that direction towards that wide radius locator. And it'll hop across a couple satellites, and all it really has to do for the software defined router for each satellite is I have to say, am I in that wide radius locator? No? Okay, pass it on. Yes, pass it down, right? That's all it needs to do. So it's a simple architecture, and it'll make the engineering much simpler too, which should help us create that scalability where we don't have to constantly be managing all this data. And especially with IP addresses, they're all like a mapping. I consider an IP address kind of like a mapping of a machine readable address to a physical locator, right? It's telling you where the locator is, and it just so happens to have an identifier within it. So This will allow you to basically uplink, downlink, and then find that wide radius locator, right? Which is mapping it to that physical locator. And then it's going to downlink to a ground station within that wide radius locator. And it'll know the ground station that it's looking for because, for one, it's within the wide radius locator, and two, it knows the identifier of the ground station, which is part of the wide radius locator information. And so then it finds that specific area, and then it downlinks that packet to those ground stations. And then this is where the re-encapsulation comes in. Let's say that ground station is connected to Victor through IP. So that ground station's geospatial locator, or IPL, IP address, Internet Protocol Locator, will be the locator that's appended on. So Victor, let's say he has a geospatial locator register and he has an IP locator. So you can have a little switch to say, do we prefer to go over Nexus protocol or prefer to go over Internet protocol? Those decisions will be made in the implementation phases. But essentially, I can either append an IP packet header, an IP version 4 packet header on there, or I can append a geospatial locator. If I send it over a geospatial locator, I'm going to have the direction, the GPS location of where Victor is, or of the next node that knows where he is. And I send that to them. And then it hops. It'll most likely have only one hop from the ground station because the ground stations are going to form cells, and we're going to follow that cell topology so that you are registered within there. And you also get further aggregation because these 3 or 4 ground stations can have the same replicated information that can be compressed because now 4 have all the information of 1, right? So you get higher aggregation. More ground stations can be mapped in the mapping system with mapping more clients. So you have then that packet gets to Victor. Now let's say it's an IP address locator. That ground station would then put an IP4 header on and then send that over the regular internet protocol, and then Victor can receive it that way. So that's one way that we get this interoperability between them, and it's done topologically independent, which means we don't have to manage state to complete the route. The state is kind of already there. We have the GPS coordinates are mapping to the state, but the state really exists in the space-time continuum. This physical locator is this physical location, and from that, you just keep hopping. So it interrupts with the legacy IP, and it acts as another type of locator. So this locator layer is really important for one, creating this aggregation, the re-encapsulation, and the interoperating with the current internet protocol. So this gets us to the identifier layer. And this is the layer where packets are actually addressed to. So when I send a packet to Victor, what I'm actually doing is I'm sending it to his EID, or his endpoint identifier. And it's kind of like having a permanent phone number for anyone to contact no matter what network you're on. So, it's kind of doing for the internet what the phone system is doing. And this is a part of the Lisp terminology, locator identifier separation protocol. The one stack is essentially an embodiment of the Lisp protocol in a full stack that includes a signal layer and all these other aspects. And then our, individual locator systems that, Lisp does support GPS coordinates, but the underlying routing system can't route for GPS. It's an information that it doesn't know and understand. And so that's where the software-defined router is going to be really important. Is it's going to support the TCP IP stack, but it'll also support TCP NP, right? So that as you receive packets through your ground station, you're going to either be re-encapsulating them or forwarding them on or dropping them, right? So identifiers are also unique and cryptographically authenticated, meaning no one can spoof from one another. In order for you to register your mapping or to receive mappings from other people, you have to have some sort of authentication, which means that I can't just make packets come from my IP address, right? Unless I have the cryptographic key to do that. I can't claim and receive any of those packets unless I have the cryptographic keys. So this is a really important step towards, improving the security of the internet as we know it by using cryptography. And that can be authenticated off of the consensus layer, because cryptography really doesn't mean anything. It doesn't authenticate anything unless you have a point of reference. That's why you have public key databases, or blockchain is starting to become that too. A certificate authority, for instance, is a public key database, which essentially is you're paying, let's say, VeriSign to sign a certificate for you with a key that they have in a public key database that verifies that VeriSign verified you, so that you can then therefore authenticate yourself with that digital signature or that signed certificate, and then open up an SSL or a TLS connection from there. So it expands also on the 128-bit number space for IP version 6. So we're actually supporting IPv6 as identifiers so that we use 128 bits each time so that we can still interoperate with existing TCP/IP interfaces. You could send a packet out over IP, and then that mapping lookup could tell you to go to a wide radius locator that's your nearest ground station that then, as the locator comes in, it can strip off that IP and then put on a WRL and then uplink to a satellite. So, it doesn't have to go IP last. You could send the packet out over IP first. And the same thing could happen if somebody's running an old Linux kernel, is they're only sending packets to an IP address. As long as they have Lisp, they'll be able to address to them, and it won't seem like anything different. And this is going to be really imperative for all of these computers to interoperate, because the internet's value comes from our ability to connect, right? And forming more of these connections. It's called Metcalfe's law, which basically states the value of a telecommunication system is proportional to the square of the participants involved, right? So we need to maintain everything that the internet currently does in a new, seamless, authenticated way, right? So we got some old friends from the OSI. As I was saying earlier, we have the transport and session layers. They're brought in from the OSI, and protocols such as UDP and TCP are still going to be used for the Nexus protocol. So we're going to have TCP NP and UDP NP, and the session layer security such as TLS will still be utilized. And this is important for basically having the same socket interfaces, even when you're running LX over IP. You'll always be opening TCP, NP, IP to their 128-bit identifier, right? So you have this common interface. As long as you run Lisp, right, on any of these devices, you'll be able to interoperate and communicate. And that's going to be really important, because we don't want to require people to have to install this operating system to access this new network. We want to give them software that can augment the current operating system, but we also want to incentivize people to move to this new operating system, because you get all of these new positive qualities for it. So you'll basically be able to use the internet protocol or Nexus protocol as if you're using just one large internet. The Nexus protocol will begin as a type of satellite mesh ad hoc network. And it's especially most likely going to be helping people that are in, economic disparaged areas to, be able to start connecting, because one of the reasons that there's not networks everywhere is it's really time consuming and expensive to lay fiber, to lay that physical link layer, right? And there's not much economic incentive for some of these places in Africa, let's say, to get online, because they don't necessarily have the money to be able to pay for ISPs. So the conventional, client server ISP model, where you're paying for the service and you're paying for the hardware, that's going to go away with the Nexus protocol. What it's going to change into is the opposite, where you buy the hardware as an investment, but that hardware then becomes also a business, right? Where you can become your own local ISP. And some people have done it on the current internet, right? Where I've seen some people, they started their own little ISPs and stuff like that. And it's certainly possible to do on the current internet. But what we're doing is lowering that barrier of entry and basically baking that economics into the entire routing system, and also a reputation system associated with the routes, so that you can throttle packets based off of the reputation information. So, that's a big problem with the internet that happens right now. And this is one reason, from what I understand, why multicast traffic doesn't necessarily always propagate across the internet, is because, all of these large, federated companies, they all have different pieces of the internet's network. And so, it has to forward and hop through each one of these large centers, and they don't always forward multicast traffic. It's kind of this unwritten law that, hey, in order for the internet to function, we're going to have to cooperate in some way, shape, or form, which means I'll route your packets for you if you route our packets for us. But that's really only been in unicast, right? It's not really gotten, up into the multicast area. And Victor has done a lot of work on the multicast, signal for multicast. And that's one thing that actually Dino and me first started talking about. Actually, the 2017 conference is where I met him in my speech for the 3-dimensional chain. He raised his hand and said, "Hey, have you ever thought of using multicast?" And I'm like, no, not what's multicast? I mean, I at that current time was still on the session layer, right? I knew about TCP, but I never really got into the ins and outs of it. And so multicast became another really important quality. So, this is designed with multicast inherently in mind, so that, based on a certain reputation of an identifier, you're able to determine if that traffic should be forwarded. So it's kind of like a give and a take, where the more you give to the system, the more you're able to receive from it. And that's how you can provide access for people free. Facebook and Google both tried to solve the 5 billion people not connected issue, but they're doing it in a linear value stream. And what that means is, you have this, it's the client slave or this client server mentality. I market and I get a direct, increase in sales linearly to the amount that I've marketed, right? And so you have this constant relationship where it's like you put more money out to make more money, right? And you only really get linear value back, like 50% margins or 100% margins, right? It's all a linear system, but this is an exponential system, and it's designed to really capture that exponential value that you get through telecommunication systems, in a way that it allows everybody to continue to use it, right? But receive that value from it exponentially. And that comes from multiplying these different revenue streams. But one other really important indicator too, and this kind of goes down to the signal layer slightly, is that one issue we have with the current internet is that you can't break a pipe. And what I mean by that is all the cables are connected, and you still have hard switches, hard cutoffs, but my home router, for instance, doesn't have that. So if my router gets under DOS attack, DDoS, my router could actually, it won't be able to drop packets fast enough because your memory can only, work. It's so fast. So, you end up overloading this router. And then even if your software tolerates, DDoS or tries to block it, you can't do anything about it. And DDoS attacks have been a really huge issue on the internet since inception, because everything just goes through the pipe, and it really is up to the router and its hardware and software to drop those packets, right? But now that we have electronically steerable antennas, right? If somebody's bombarding me, let's say with a beam right here, I have to actually be open and pointed to them electrically to hear that. Since it's so highly directional, I just go, boop, I'm gonna look over here and I'm gonna talk to this guy. So you can actually physically cut off the packet flow with just reorienting your antenna. So what we're afforded is these really unique opportunities to basically reduce a lot of security issues that came from the openness of the internet. Is you should be available and I should be able to send you a packet. And another thing that Lisp also provides, and this is something that's built in with the one stack, is you can choose when you accept traffic, right? You can set specifications to the mapping system to say, I only want to be talked to, for these, hours of the day. And you do that through the ground station. You register with your local ground stations and you give them a set of conditions to say, I only want my, IP address to listen for traffic, or to be open to forward, incoming traffic to me for 9 to 5. And after that, I don't want to hear anything. Or, I want to say, I only want to hear from these 3 identifiers, my family, after hours. And then every time else, other people can do it. So you create these really cool, like phone, specifications where you can, in a way block a caller or, ignore someone or mute and things like that. And that's what the mapping system really affords us, right? Which is really important, because it's taking that privacy and usability of the internet to this next level. And it's really taking Lisp and the Lisp architecture, and it's weaving it into its own type of OSI, right? And that's, the one stack, the one reference model. So getting to the consensus layer now. The consensus layer is responsible for essentially creating a layer of trust on both Internet Protocol and Nexus Protocol. So it's a common reference point of truth for managing root of trust, such as security certificates. So right now, when I make a connection, let's say I open up TLS, I receive their certificate, and I need to verify with the certificate authority that is actually a valid certificate produced by them, right? Otherwise, somebody could be masquerading as anyone else. A cryptographic key only tells you there's a mathematical relationship between the private key and the public key and the signature. That's it. Right. So anybody that says cryptography is used to identify things, and I've seen Vitalik say that numerous times, completely wrong. Cryptography does not identify anything. All it does is shows a mathematical relationship between 3 pieces of data: your private key, which generates the signature, your public key, which is used to verify the signature, and the signature itself. So when I generate a signature, I'm producing this signature and this public key. And then anyone else, Victor, would be able to say, okay, I can see there's a mathematical relationship between this public key and the signature, so I can verify that you have that private key. So that doesn't mean anything until you have context, right? The context comes from our consensus layer. Instead of relying on third-party databases and key servers like we have currently with the internet and certificate authorities, you rely on this decentralized ledger. So you get automatic authentication between users. So what your end result of this ultimately in layman's terms is when you're talking to someone, there's no shadow of a doubt that that person's computer that you've talked to is that person. You can't verify that like a human is actually the human, because it's, you only have state up to the computer, right? I mean, and you trying to figure and do that is just, I think, a waste of time, because you get into privacy, violating issues with face recognition and stuff. So we're not identifying the actual physical person. We're identifying the person's common computer address that you're talking to. So, Victor and me would know anytime that we open a communication channel that he is indeed Victor, and there is no man in the middle attack, right? And this is really, really important, because that increases our security of encryption, increases our security of identification, and it also removes so many different cases of fraud, especially when we're talking about a new financial system. Chargebacks are a huge issue for merchants. And people spoof IPs, they use VPNs, they hide, and the internet kind of has become this like shadowland in a way of, hiding, right? And we're kind of taking it to another level where you still retain your privacy, but you can have more trust on the internet without sacrificing anonymity, because the identifiers and cryptographic identities of people that you're interacting with. You may not know who they are, but you're for sure talking to the person you're intending to talk to, right? So the consensus layer is composed of 3 layers from the Nexus Software Stack: the ledger, register, and operation layer. And the ledger is responsible for chaining of cryptographic data, and that's where we get the immutability. The register layer, is like a little data object that kind of sits on top of the ledger, and it actually can move. Like if we have 2 sig chains, a register can sit on top of a sig chain and move between sig chains, right? That's kind of how it basically works. And then you have the operations layer up here that gives the registers context. It's an operation that says, hey, move this register over here, or transfer this, or modify its data, or things like that. So as you can tell, these little registers can be used to store important metadata, right? And some of that important metadata is actually hashes of keys. One of the things that we have is called the crypto object register on Nexus, and that happens on the ledger and the register layer. It's a simple little register that just contains a bunch of hashes, and all of these hashes hash of a security certificate or a key. So what ends up happening is when Victor sends his certificate to me on the Nexus protocol, I will hash that certificate and then do a lookup on the ledger and read his crypto object register and check that the hash of the certificate I've calculated is the same hash that he's published in his crypto object register. And from that, you have authentication, and you don't need security certificates, which means you don't have to buy a new certificate once a year from VeriSign and pay all this money and domain verification and all of those things, right? Those are first steps towards authenticating things, but really they're higher level architectures that were built as layers of indirections on top of the existing infrastructure. And what we've really done is taken all of these things that we've learned through the internet, and we've dropped it into a totally new bottom up architecture that's built from the ground up that, addresses all of these things in the initial foundational architecture, right? And that's really ultimately what the one stack is it's addressing all of these, how should I say it, pitfalls that we've learned over the years in a very simple to use interface, right? So this is where you get the open Nexus execution aspect of it, because the consensus layer or the operations are able to mutate the state or execute something. So we not only have an internet now that we can communicate end to end, but now we can engage in contracts and execution on top of that through the consensus layer, which could mean engaging in geospatial contracts, such as I'm going to put 100 Nexus in this wide radius locator as a geospatial contract that has a certain set of conditions to be met. Let's say you deliver this file for me. I want people to deliver my video that I just recorded in Phoenix, and I want that video to constantly be distributed out. So I'm going to put 100 Nexus in a wide radius locator. And then anybody that has a ground station in that area will pick up, hey, I'm within this wide radius locator. Oh, I want to engage in this contract and deliver this data for that specific individual. So geospatial contracts also create new types of marketing opportunities. And this is when we get into these exponential value streams and how the value can multiply itself, because you not only have real estate, right, of where you're living, like, hey, I'm close to the shops or things like that. But when you're closer to other people, you have a next level of that where you can actually start monetizing it through geospatial contracts, right? So it's going to add a whole new dimension to real estate and location, and what it actually means, because now your location is going to have some sort of, monetary incentives. You're going to be able to earn a passive income just from having a computer in that wide radius locator. And that will also allow different organizations to say, I want to put 100 Nexus in this geospatial contract or this geospatial locator in my shop, and say that you have to walk in my shop and buy one thing and then you get it, right? So you create these totally new economic marketing opportunities where people basically can, in a real live interaction, interact with these contracts, right? And that's something really important for making that bridge between crypto land and the real world, right? A lot of these crypto smart contracts aren't necessarily fully applied in the world. A lot of them are speculative. People are mainly doing it to earn money. But when we add this and tie this into this entire new routing system, and then weave that through all these new contracts, we're going to see interactions in ways that I'm sure I have not even begun to think about. And that's the beautiful thing. You know, that's going to be a huge change for people. And you know, the fact that it can remain free or very low cost, and that it's peer-to-peer, and that you don't have ISPs, and that your hardware, instead of being a money sink, actually becomes something that earns you money, it's going to change the entire game. It's going to change the entire economic system. And so since the ground station, ground infrastructure, and the satellites themselves are essentially driven through these economic principles, it'll build itself. We don't have to build this new internet. That's where this architecture has made this Nexus protocol so practical now, with this ISM frequencies and everything else, is we simply just need to build this operating system and, you know, deploy some initial hardware and take it off and let it run, because, you know, it's incentivized. You know, why would I go pay $70 a month for an ISP and then pay another $50 for the router, when I could just go pay $100 for, you know, a Nexus ground station, or a few $100s. These numbers aren't, you know, committed, so don't take those as the actual numbers. I'm just spitballing random numbers, but, you know, let's say a few $100s for a ground station, and now I can earn money from engaging in geospatial contracts. Like, why wouldn't I do that? You know, especially since it interoperates with the internet protocol. So, you know, I envision that as this really proliferates and it really grows, I think we're going to see a lot of people being able to utilize it, but also it levels the economic playing field. People around the world are just held in different economic disparagements through hyperinflation. And that's one reason why the internet hasn't fully proliferated, because there's no economic incentive for people to deploy these networks. But now that there's no physical infrastructure required other than just buying ground stations and, you know, linking them to satellites, people in impoverished areas will be able to start crowdfunding together and get a ground station as a community and share that and create a local community Wi-Fi and allow them to connect in ways that they haven't connected before. And on top of that, be able to use Nexus to earn, you know, passive income, because these ground stations will be able to lease some of their disk space and engage in geospatial contracts through content delivery, edge computing, or even just hosting, and earn passive income just from having a computer on. Right. So we take this mentality and we flip it on its head, where it's like, I pay for hardware, I pay for electricity to use the hardware, I pay membership fees, I pay service fees, I pay software fees, and out, money going out, to I buy this hardware and now it brings money in. It's kind of synonymous to Bitcoin mining on an internet protocol. Think about it with Bitcoin miners on an internet protocol, where you buy this hardware and you have a direct return on investment capability. So the Nexus software stack, as you can see, this is how it interlinks with the OSI, right? The OSI, as you see, the physical data link, network transport, session, presentation, and application. That links in together with each of these, right? And the network layer is the lower four. So I wanted to show you this as a little context so that you could see how that fits in with LXOS, which stands for lower level library, L4, and Lisp. I know it's a mouthful. It used to be LLOS, but we found LXOS sounds much better. So the lower level library is a polymorphic template library I've been developing since about 2014. It includes a constant time database, which means a database that doesn't slow down as you add more data to it. Conventional databases slow down as you add more data. If you notice, Bitcoin gets slower as you add more transactions. Ethereum gets slower as you add more transactions. The lower level database, part of the lower level library that I've developed, does not. I've tested it up to 400 to 500 million keys, and it does not slow down. It stays constant time through the entire process. So it's really important for having a sustainable architecture and a sustainable system when the data set's constantly growing, right? You're just, with current blockchains, legacy blockchains, it's just this ticking time bomb. And that's one reason why, you know, Bitcoin has been reduced in its, you know, capacity, you know, even though Moore's law, right, is an exponential construct. And so Therefore, disk space is always increasing exponentially, but yet the blockchain is only increasing linearly, which is one thing that Satoshi, envisioned for Moore's law being a scaling solution. It still has limitations in quantum tunneling and parallel processing. You can only verify so many ECDSA signatures per second, and there's only so much data that can be fit through the pipe, right? And your database always is going to start slowing down. So there's all these other software issues that needed to kind of come together. So this operating system is kind of this is my final gift to you all for computers, right? There's just no more I can do with computers after I build this operating system, because that's it. And it's really important too, because for digital freedom, we have to have an operating system that we can be safe in, right? So this it's basically originally being developed for cube satellites and IoT devices first, as a beginning stage for improving basically IoT security and development of IoT and the initial formation of the cube satellites. And then it virtualizes the user space through distributed computing. So what that means is that your computer is no longer going to be tied to just your computer. Your computer is going to therefore be something that exists, in Nexus, in this hyperspace, so that you can take your physical device. I can take my phone, go throw it in the lake, and then log in to Nexus again on the operating system, and boom, I'm back, right? It just repopulates your local cache. So, since the world is moving towards a cloud, this is kind of like a private decentralized cloud, but without the cloud control, right? If we've all seen Parler got deplatformed from AWS. I mean, just for having a certain political affiliation, and the corporations, did not like that. That's one reason centralization is an issue, because anybody can, censor anything out. So this is an uncensorable cloud, and it's also a cloud provided by your peers. So you can engage with people of your same level, not paying it to this big corporations. It's going to use that money to further try to enslave us. It's going to be something that allows you more of that digital freedom and empowers your neighbor while empowering yourself, right? So briefly on the ledger layer, the ledger layer manages ownership of registers, and it's responsible for chaining data into immutable objects, and it's verified through locking mechanisms validated through global consensus, right? And it essentially is proving ownership and permissions of registers on the layer above. Now we get to the register layer. The register layer are state objects, essentially, that holds the data owned by each specific participant. So they can be transferred, written, or used as proofs on the operations layer above. But object registers are also type-safe programmable objects, allowing the creation of custom data types. Currently, they support polymorphism, and with augmented contracts, we're going to be adding methods. Now, registers can point to one another, forming a relational database model, right? So essentially, a name, if you've ever used the names on Nexus where you're sending to someone's trust account, that's a layer of indirection, which is a relation from one register to another. And it's kind of like a DNS system. It's called TNS. And that allows you to basically take a register that hashes to a specific name and point that to a specific piece of data. So these object registers and these name registers and this TNS, which stands for Town Name System, can also be further applied into DNS, right? All we really need to do is get a web browser to start implementing our TNS protocol. And we're also going to add in essentially a DNS management system through TNS. So what we're doing with security-focused operating system design, right, is we're doing runtime and memory binary verification. So we're verifying the specific states of the operating system to ensure that nothing can be corrupted or tampered with in the process of anything happening on the operating system. So, your file system won't be able to be tampered with. The binaries are going to be verified. It's kind of like what Windows is trying to do with their new layer of security on top, where you have to have notarized binaries and stuff like that. But that really just moves the attack surface to the Windows key server. It doesn't really do anything. It's kind of like adding lipstick on a pig, right? Fundamentally, operating systems from the ground up need to be re-envisioned. And that's why when I said L4, that stands for L4 microkernel, which means we're using the SEL4 microkernel, and we're going more towards a microkernel architecture, which originally were not very well accepted by the world because they were slower than monolithic counterparts. But since we have had an extremely large improvements, especially with the L4 stack itself, and that has allowed people to start to really see microkernels get to the point where they compete with their monolithic counterparts. For a frame of reference, a monolithic kernel has everything in the kernel, right? It's all one big blob, one big component, and that's Windows, Linux, and OS X. A microkernel is a small little kernel where it doesn't really manage policy. It just has small little things that it does. It does threading and not even memory management. It's just very, very, very basic. And the SEL4 microkernel is like 10 or 20,000 lines of code, right? So it's extremely simple and it's extremely efficient because of that simplicity. And so therefore you can get really high security qualities from that. So when we do runtime memory and binary verification, we're authenticating every aspect of the runtime environment, and we're requiring a user action in order to authenticate specific methods. So we use memory randomization, but more importantly, only small sectors of the page memory will be executable, right? So you have to have user action and verification of the binary in order to move forward and execute anything. So what this does is it makes this operating system immune to most conventional cybersecurity risks, which is really important for any type of application, especially in the satellites. So runtime's instructions also must be authenticated with a register allocation, and newly downloaded binaries will be authenticated from developers' signature chain, required, that authentication before actually executing. So this is essentially going to make it so you can't just click a link and get a virus. Viruses, they inject themselves into your local file system, or they mutate your runtime memory, or they manipulate your stack, and that's how they get in. Because the operating system doesn't really know and authenticate itself. This operating system will, which means we essentially add privacy and take it to the next level, because now it's not only something that's focused on privacy and everything's encrypted, but it's something that nation states can't attack, right? Security vulnerabilities, a lot of them have been manufactured backdoors. If you remember the Heartbleed in OpenSSL, whether or not that was manufactured, it crippled the entire internet infrastructure. So this will, ultimately make your computing safer, but it's also going to allow you to execute things that exist already, such as your Windows applications, doing that through a hypervisor, right? So really quickly, the file integrity Merkle trees authenticate your file system. They disallow that from being tampered with. So you can't inject these viruses into the file system. A virus is kind of like a virus in a body, where it's injecting RNA into your host cell and causing your cell to replicate that RNA out. A virus doesn't necessarily do that. A worm does that to replicate itself, but a virus usually hides in your file system somewhere. And that's why you have to scan all of your files to find that little bit of binary data that matches that virus, right? So this will not be possible with LXOS, right, in the one reference model. And then the final thing about software-defined routers is really important, because, IP version 6 is a perfect example of what happens when the hardware actually can't be updated. And so, we only really, it's been around for 20 years, but IP version 6 still hasn't proliferated to the rest of the world. As you saw in Victor's speech, it was 10 years to get TCP/IP updated, even on a small network. So things need to be software-defined, right? Software-defined satellites and software-defined routers, so that in order to update the routing protocol, just click a button, right? It'll automatically update, automatically have that state, and that will be built into this operating system, right? Now, we're also going to authenticate our ART packets, and we're going to authenticate everything up and down this OSI stack, right? And the one stack, in order to make sure that nobody can tamper with anything and nobody can say or masquerade as something that they're not. So this combines together, as I was saying, into our stateless routing system that it essentially allows us to handle dynamic routing systems without having to have a constant updating of IP addresses, right? We're all addressing to the identifier, and then you have locator re-encapsulation for each of the packets as it moves through the path, so that you get interoperability and you get a same common interface, and it's stateless, so that you don't have to constantly update this information in these satellites. And as the low Earth orbit satellites are constantly moving, you can't have a static routing system for it. So now, finally, is we got to authenticate everything, right? We want every aspect of the operating system to be authenticated through immutable source of truth, which is our consensus layer. We want to protect the CPU instructions, We want to check every one of these operations to make sure people can't mutate or manipulate any aspect of the computer, so that when we get to consumer grade, you can fairly confidently feel that even if people make viruses for it, they're not going to be effective against it, because the system will know itself, the kernel will protect itself. You'll know if there's any RLP vulnerabilities, buffer overflow. It'll also protect against programmers making those mistakes, such as overflow vulnerabilities, which, is the 1990s way to take down any system. You do an overflow, and those still exist. And blockchain, in a way, has reintroduced all those security vulnerabilities all over again. So we want to make sure that we eliminate security vulnerabilities with this new technology, not recreate the same ones, right? So we have to authenticate everything. Then finally, we have device level identification, which means every satellite itself will have an identification associated with it. And it will tie in with the Locator identifier separation protocol, so that specifically not only the device, but the person, and that it's a safe, secure communication channel. We'll support quantum resistant cryptography such as Saber, among other things. And then the final point is the virtualized user space, where your computer will no longer be bounded by your hardware. Your computer will exist in this decentralized cloud, some of which will exist on the satellites, and some of it will exist on the ground infrastructure, so that you can reliably not only have a secured computing environment where you can, have certain guarantees of, protection against certain types of attacks, but you will also not have to worry about backups anymore. And you won't have to worry about backups of, your cloud provider censoring you, right? Your computer will no longer exist on the hardware. Your computer will exist across this network in a virtualized user space. And the physical hardware will only just be populating that local cache. So the conclusion is that we authenticate every user action of the operating system, and we protect against buffer overflow exploits and in the injection techniques, and we virtualize the user space so the computer exists more in a mathematical hyperspace than on the local disk, and we authenticate every device and develop software-defined routers so every computer becomes a node in the mesh network.